Hello everyone, I'm Kheirandish from the University of Nevada, Las Vegas, and today I'm going to talk about IceCube's observation of high-energy cosmic neutrino flux. The universe is very rich in neutrinos, and neutrinos present the most abundant constituents of matter in the universe. Similar to the photons and electromagnetic spectrum, neutrinos occupy a broad energy range across the sky. At the lowest energy, below milli-electron volts, we have the cosmic neutrino background that are the relic neutrinos from the early times in the universe. And these neutrinos have a high intensity compared to the other components in the neutrino sky. However, because of their low energy, they are very hard to detect. As a result, what you see here is a prediction for the CNUB. As we progress to higher energies, the magnitude of the flux decreases, and we reach to at keV energies where the solar neutrinos are the dominant component in the sky. These are the neutrinos that are produced in thermal and nuclear interactions in the sun. And as we continue towards higher energies, we have the neutrinos that are produced in the supernova. You see here on the plot the neutrino flux observed from supernova 1987. That's the neutrino observation that was made about 40 years ago. And this is the latest supernova that we have observed. This was in the vicinity of our galaxy, but we are still awaiting the supernovae that should happen in the Milky Way. It will produce a large amount of flux compared to the other components, but although we haven't seen any other supernovae, we know that the galaxies and do have supernovae in them. The rate actually increases as we go further from the Milky Way. And they generate a diffuse background of neutrinos at MeV energy, which is the diffuse supernova background. This is not seen yet, but you see the prediction here with a lower magnitude in flux. But the talk today focuses on energies beyond GeV. And this is the realm of atmospheric, astrophysical, and GZK neutrinos. The atmospheric neutrinos are produced in the cosmic ray interaction in the atmosphere, producing charge and neutral mesons that promptly decay and produce neutrinos. Astrophysical neutrinos are similarly produced in astrophysical beam dumps. You have a cosmic ray that is accelerated. It hits some target, would it be radiation or matter? And then it produces charged mesons that will eventually decay into neutrinos. This is what IceCube actually is seeing. So the line that you see is one of the IceCube measurements. At the highest energies, we have cosmogenic neutrinos, also referred to as GZK neutrinos. These are the result of ultra-high energy cosmic rays interacting with the cosmic microwave background. This results in a cutoff in the ultra-high energy cosmic rays. We don't see cosmic rays after some energy, but this has been predicted more than 50 years ago. And this was considered to a point one of the guaranteed components, and it was soon realized in order to observe the neutrinos that are generated by an astrophysical flux at PeV and beyond energies, you need about a cubic kilometer detector to find at least one event. That was the requirement that was established early on, which resulted in a lot of attempts to build detectors that can actually find these neutrinos. Another important aspect of neutrinos and the universe is that neutrinos become one of the messengers that actually arrive to Earth at certain energies. After 1 TeV, depending on what distance you look, you start losing the gamma rays that are produced in the universe. So the universe at PeV energies beyond the Milky Way becomes basically dark in terms of the gamma rays. Gamma rays cannot arrive at Earth because they will start cascading down by production of electron-positron pairs. So this realm is basically only belongs to neutrinos, cosmic rays, and gravitational waves. Cosmic rays, on the other hand, cannot reach directly from their sources. And that basically necessitates doing neutrino astronomy if you want to identify the source of the cosmic rays. And in fact, it was realized soon after the discovery of of neutrinos in 1950s that the neutrinos are actually ideal cosmic messengers because they are hardly interacting, so they are not absorbed by the matter between their sources and the Earth. They are neutral, so they can point back to their sources, and therefore they can provide the smoking gun for the sources of cosmic rays. And as mentioned, in the absence of a detector like LISA, they are actually the exclusive messengers at a certain distance in the universe for 10 TeV to 10 eV. And this all makes neutrinos ideal for doing astronomy. However, we know that as ideal that neutrinos might be for this purpose, neutrinos are very elusive. Because of that, we are dealing with low statistics, especially since the flux is very low, as you saw in that plot earlier. And we have a large background, as we will see later. And this was basically a challenge for neutrino astronomy, requiring immense detectors. But how do we see those high energy neutrinos? The observation basically relies on the Cherenkov light that is produced by charged particles traveling faster than the speed of light in a transparent medium, such as ice or water. We can see one of those interactions here in the Feynman diagram. You have a charge current interaction of muon neutrino, for example. It will induce a muon. That muon is long-lived enough to travel few kilometers in the ice and pass through the photosensor arrays that you build there to observe the Cherenkov light. This enables you to identify the energy, measure the direction, and the arrival time of the neutrino. And where to put such an array of light sensors? As mentioned, you need a transparent ice. And the best ice that you can find on Earth is at the geographic South Pole. It is an ultra-transparent ice below 1.5 kilometer of the South Pole surface. So we built IceCube exactly at the geographic South Pole. What you see here is the IceCube lab. It sits on top of the detector that is actually buried about 1.5 kilometers below the surface. This is the schematic of the IceCube. It is the first cubic kilometer neutrino telescopes. These predecessors did not have the required volume, but they basically paved the way by proving the concept of a neutrino telescope in the ice or water. So the detector consists of 86 strings. Each string has DOMs, which are digital optical modules. Each string has 60 of them. They are basically buried in these holes. You see one of the DOMs going down the hole on the cable. They consist of a photomultiplier tube that collects the light and a CPU and a computer on top that can basically transfer the digitized information to the IceCube lab on the surface. The detector goes down until 2.5 kilometers. The main detector, the IceCube array, is more or less hexagonal shape, and it has the sensitivity to neutrinos with 100 GeV and greater. There is a sub-array called deep core, which sits at the middle of the detector. It's a more dense array of strings, and it has a lower energy threshold. It can actually collect neutrinos with energies of few GeV. Okay, so IceCube was deployed by 2011. After completion in 2012, IceCube actually succeeded in identifying the promised neutrino flux as the prediction had asked. But before we talk about the observation, let's talk about the detection principle. As mentioned earlier, the detection principle relies on the Cherenkov light that is produced by the charged particles traveling faster than the speed of light. But depending on what type of interaction happens, you would have different morphologies in the detector. If if you have a charge current interaction of nu mu, which results in the production of a muon, that muon lives long enough to travel long distances in the ice. If it passes through the detector can collect the light that is produced along the path of that muon that passes. The light looks something like this. Is a long arm. We call them tracks. This is an upgoing track. Basically, came from the northern sky. So basically, it was come through the Earth. And the color here indicates the time. So this is earlier. This is later. So this basically tells you the direction. And as it is a long array of light, you can reconstruct the direction very well. So the angular resolution for a track is better than 1 degrees at 1 TeV, and it can get to better than 0.3 degrees at 100 TeVs. But since the muon can deposit some of its energy before or after the detector, the energy resolution is not as good as one may hope. So you have about a factor of 2 energy resolution. Another type of event that can be produced is a result of neutral current interaction of any flavor of neutrino or charge or neutral current interaction of an electron neutrino. This results in production of a lot of charged particles, mostly hadrons, and electrons that are not propagating as much as the muons. As a result, you see the propagation of the light spherically inside the detector. If the interaction happens within the detector, it means that you can basically collect all of the energy that is deposited. We call these event showers or cascades, and it has a very good it has a very good energy resolution because you collect all the deposited energy. But since it doesn't have that lever arm, you cannot reconstruct the direction as good as you do for tracks. So the angular resolution is about 10 degrees. Another interesting feature is charge current interaction of nu tau, because it produces a tau particle, and the tau lepton is very short-lived. It would decay inside the detector. So the first interaction creates a cascade. As the tau travels towards this right of this figure, it again decays and produces another shower, and you will see 2 showers from one event that is called double cascade. And this is a distinct identifier for nu tau. So now that we talked about the detection principle, we need to identify the signal, basically the neutrinos that are produced by the astrophysical flux that is not produced in the atmosphere. Basically, it's not terrestrial. So the main background for us is the atmospheric muons. These are produced by the muons that are generated by the decay of pions. They have high energy. If they are generated close to the surface of the Earth, close enough to the surface of the Earth, they would not decay to neutrinos, and you would see them as muon tracks in your detector. And it is actually an overwhelming number of them. It's about 10 to 11 per year. The second background component is the atmospheric neutrinos. They appear at a lower rate, but still there's a lot of them. We get about 100,000 atmospheric neutrinos per year. The astrophysical neutrino, which is what we are looking for, is at much lower rate. And we expect about 100 to 200 muon neutrinos per year. So this is basically looking for a needle in a haystack. However, we have sophisticated techniques to reduce the background and reject them in our search. In order to do that, we utilize 2 different techniques. One is looking for isolated neutrinos. These are the events that are happening within a defined fiducial volume of the detector. So in the outer layer, anything that has a trace of trace is not included because it is more likely that it is coming from the atmosphere. But if the event is actually happening inside the detector with a specific amount of charge, it is an identifier of purity of the event being astrophysical. You can do this for all flavors. And the other way is to use upgoing muon tracks. Upgoing again means that they are coming from the northern sky, which means they are passing through the Earth. The Earth acts as a shield for the muons that are produced in the atmosphere. So you can overcome the majority of those muons that are overwhelming you in the detector. Using that, then you can basically characterize the atmospheric and astrophysical neutrinos and see if we can have a component that cannot be described by atmospheric flux. This was done, and both channels, both techniques have found the astrophysical neutrino flux. You can see them in these two, with these two lines for the muon neutrinos and for the HESI, which is the starting events. In this plot, you also see the atmospheric muon neutrinos, atmospheric electron neutrinos, and the prompt component that is produced by the charm production in the atmosphere. The first two, the atmospheric muon and electron neutrinos, are observed. We have not so far observed the prompt neutrino. But the astrophysical flux have been observed where we have the ability to veto the atmospheric neutrinos, or the astrophysical component becomes dominant over the atmospheric neutrinos. The high energy starting event was the one that actually provided the evidence for the astrophysical neutrino flux in 2013. It finds a flux that can be described by e to power minus 2.89. 7.5 years of data reject atmospheric origin of this flux by a significant 8 sigma significance, and it consists of about 100 events from all flavors. The other channel, the upgoing muon tracks, finds a different slope. It finds a flux with the power law of minus 2.37. 10 years of observation yields a significance of rejecting the atmospheric origin by 7 sigma, and it actually consists of 600 astrophysical neutrinos, most of which are actually buried under atmospheric neutrino flux, and we cannot single them out. There are limits on the cosmogenic flux, that is the GZK flux that is produced by ultra-high energy cosmic rays, by IceCube and the Pierre Auger Observatory, and also other experiments. This is still being sought, and we have not seen it yet. When we look at the part that we have observed, the cosmic neutrino flux, there are two main things to note. First, the fluxes have a different slope, but they are compatible in the common energy range. The fact that you see different slope and the increase at lower energy here hints at potential features in the spectrum that can point back to different source properties. And this becomes very important in terms of the progress that we have in identifying sources of high energy neutrinos. Here, you can see the arrival direction of the most energetic neutrinos. These are events with events greater than 100 TeV. They are not likely to be atmospheric. And as you can see, they are scattered across the sky. These are not associated with the Milky Way. This basically tells you that the flux is predominantly extragalactic. Otherwise, the events should have lined up along the galactic plane. And you can see that the Earth absorption makes the number of events that you see on this side of the plot in the shaded region scarce. But how do we go after the sources? We don't just look at our highest energy events, because as you saw, they are limited by statistics and they do not cluster. We utilize all of the events that IceCube can see. So in this plot, you see 1 year of data from the muon neutrino sample. This is all events with energy greater than 100 GeV, and there is about more than 130,000 neutrinos in 1 year. Only about 200 of this is actually astrophysical origin. The way that we look for their origin is to find clustering of the events, because the atmospheric neutrino is essentially isotropic. any excess that you find in this sky map should be explained by astrophysical component and is an indicative of a source. So before we talk about the techniques that we use to find the sources, let's talk about what are the possible sources. You need two basic qualities in a source. Two conditions should be met. First, the source has to be able to accelerate cosmic rays to beyond PeV energies. The neutrinos that we see in IceCube are TeV to tens of PeV, and cosmic rays should have at least 20 times more energy than the neutrinos that we see. So the sources of the cosmic neutrinos should be able to accelerate particles to those energy. The setup is very similar to what you have in an accelerator experiment on Earth. You accelerate particles, so you need to have all the requirements like the magnetic field and energy that you generate here. And then you need to provide the beam dump, so to produce pions and then neutrinos. So the astrophysical sources that we consider to be the sources of cosmic neutrinos should have enough density in their vicinity to produce pions that would induce neutrinos by their decay. The main suspects in this scenario are supernova remnants because they have the shocks accelerating and propagating through the galactic medium. The gamma ray bursts because of their high and enormous amount of energy that they release when they happen. And active galactic nuclei because of a lot of interesting interactions and scenarios that happen to them. And I can tell you right now that they are the prime candidates here. They have a supermassive black hole at their center. They usually have the jets of particles leaving them. They have the corona, which is very hot and turbulent. And they also have accretion disk that feeds this jet and corona and the black hole itself. So they have suitable environments for production and interaction of cosmic rays. And there's an important thing to note also about the connection between the pionic gamma rays and the neutrinos. Every charged pion is accompanied by neutral pions. Those decay to gamma rays. At the source, you can relate the rate for the two if you know the ratio of the charged to neutral pions, basically described by this K pi here. And the energy of the gamma ray is basically twice the energy of neutrinos. So you can relate the rate Q here of gamma ray production to the neutrino production. This is at the source. While after the gamma rays are produced, depending how opaque the source is or if this is transparent, gamma rays will start creating pairs and cascade down. So when we want to consider the gamma rays that we see at Earth for a distant source or for the source that is opaque, we need to take into account the cascade and suppression of the gamma rays. So we do point source searches in IceCube in multiple ways. First, we look for clustering of the events. This is when we look at every point in the sky and try to find that clustering that could be indicative of an astrophysical source. This is a pricey thing because you have to look in many places and it costs the cost of a lot of trials that you accumulate and you have to penalize for that. A more effective and sensitive way of doing this kind of search is to know a priori where to look in the sky. This will reduce the number of trials. You identify sources that are interesting across the sky for based on the model predictions or any other property of the source, and you run and try to find if you can cross-correlate the neutrinos with them and find an excess. Another way that we do this is to do a stacking search. We search for collective neutrino emission from a catalog or selection of the sources with similar properties. It is very good for testing models. It will reduce the number of events that you need for identification per source, but it heavily depends on your assumption and the correctness on your model. We also do real-time analysis based on the interesting reports that we receive from other experiments and telescopes, and we also issue alerts letting know other experiments that we have seen something interesting. So now we have used all of these methods, and this is the most recent result from IceCube. IceCube 10-year point source analysis using northern tracks, basically muon neutrinos that are coming from the northern sky. This is a time-integrated analysis, so we're looking at the steady sources, and you can see the p-value map of across all the sky. The green shaded regions that you see here are the result of the all sky scan, that clustering, that the first method that I mentioned. And you also see three sources here. These are the three most significant sources that we searched for among 110 sources that were pre-identified based on the gamma ray observations. Interestingly, NGC 1068 that you see here is the most significant source in that list, and its location also coincides with the hottest spot in the northern sky, which gives you a p-value of 4.2 sigma. This establishes NGC 1068 as the most significant source and as the first study source of astrophysical neutrinos in IceCube. Let's talk about what NGC 1068 actually is. So NGC 1068 is an active galactic nuclei. So it has a supermassive black hole at its center and accretion going around it. You can see the Hubble picture here. In fact, it's called a Seyfert-2 galaxies, which means it doesn't have a very radio loud, it's not very strong in radio emission, and it doesn't have a prominent jet. It actually has a jet, but it's not as prominent as other AGN. The more interesting thing is that it has a heavily obscured nucleus. It is one of the best studied AGN and played a major role in our understanding of AGN. And it has a Compton-thick environment. That is, it has a column density at the order of 10 to the 25 per centimeter squared. This is very large. And it is bright and X-ray. It is at high infrared luminosity, which basically tells you that it has a lot of star formation activity in it. And because of all of this, it has been historically considered as a promising cosmic ray accelerator. An IceCube observation proved that to be wrong. So let's look at the NGC 1068 spectrum. IceCube identified 18 neutrinos in the direction of NGC 1068. Based on that, we observed this flux of high energy neutrinos. It can be described by a power law with an index of e to the power minus 3.2. And this is muon neutrino flux. It is compared to two different models that try to explain the emission with the coronal activity, basically very close to the core of the AGN. And we see how that is actually important in the next few slides. So you can see the broadband spectrum across different wavelengths, a radio, optical, X-ray, which you can see the X-ray is very high and comparable to the neutrino flux, and then the gamma ray measurements. And there is an important aspect here. The neutrino flux is about 2 orders of magnitude higher than what Fermi and MAGIC are reporting. So MAGIC has upper limits. Fermi has actual measurements at lower energies. But you see that the neutrino flux is much higher. This tells you that the gamma rays that are produced simultaneously with neutrinos should be absorbed and obscured in the source. So first, if you try to model the emission from the source based on Fermi observation, you cannot explain the IceCube neutrinos. Second, you need a very dense environment, which, as we saw earlier with the column density that is reported for NGC 1068, exists there. And another important information that we get from this obscuration is that the neutrino should produce within a radius less than, at most, 100 times of the Schwarzschild radius, so very close to the core of the AGN, and very near the black hole. So this realization actually is in accordance with what we see in the IceCube neutrino flux measurements. In this plot here, I'm showing 3 main channels that we have observed the neutrino flux so far. You saw two of them before, muons and the high energy starting events. You will also see the cascades here. And the important feature here is that you have about an order of magnitude higher neutrino flux compared to what you find at PeV energies, at energies of around 30 TeV. This we refer to as medium energy, and this medium energy excess, this high level of flux, is important when you want to compare what the gamma ray experiments see. So you can see here, if you cut off at low energies the IceCube measurement, the amount of flux at 30 TeV is high enough that the intensity of the gamma rays that you produce would saturate the Fermi measurement of extragalactic gamma ray background. If that happens, you are going to overshoot what Fermi sees. So in order to be able to be consistent, the gamma rays should not leave the source and should be cascaded down and absorbed to lower energies. This obscuration then is dictated by the multi-messenger connection between gamma rays and neutrinos, and these conditions are actually met in active galactic nuclei. This is why active galactic nuclei are the primary candidate for production of high energy cosmic neutrinos. So learning from this, we started looking into sources very similar to NGC 1068, bright Seyfert. And by bright here, I mean bright in X-ray, intrinsic X-ray flux, which is an indicative of what's happening inside the core of that AGN. We ran the test for the northern hemisphere with 27 bright Seyfert galaxies. You can see the expected flux in this corona model for them. And among the 27, we identified excess towards two of them. For the rest, we have an upper limit. But these two, in addition to NGC 1068, show some excess. They do not reach the 3 sigma level. However, the binomial value trying to quantify how likely is that this excess is just from random coincidence, finds 2.7 sigma. If you include NGC 1068 in a posterior calculation, you would find a 4 sigma for the excess that is identified in the direction of these three sources. One of them is quite interesting. We find it at the level of 2.9 sigma. And the NGC 4151, which you can see its localization and p-value map on the left here, is very similar to NGC 1068. It has a high intrinsic X-ray luminosity. It is a Seyfert galaxy. It is very nearby. And you also can see the excess that is identified in its direction versus the angular separation. And while this is the second most significant steady source in IceCube, I should remind you that this is the status that NGC 1068 had in 2020. With an improved analysis, we reached to that 4.2 sigma. NGC 1068 was initially identified at 2.9 sigma significance in a previous analysis. We are doing also a southern sky analysis with a newly established event selection that uses starting tracks inside the detector. It has a good purity of event, but a little lower stat. But this good purity and astrophysicalness of the events gives enough sensitivity to observe collective emission from these sources. And it is very important in the sense that most bright Seyfert galaxies actually reside in the southern sky, not the northern sky. So we talked about sources similar to NGC 1068. There were two other sources on the sky map that I initially showed you for the 10-year analysis. The second most significant source in IceCube state was TXS, but this source was actually identified before NGC 1068 after IceCube issued an alert for a 300 TeV neutrino that was observed at September 22, 2017. This event had a very high chance of being astrophysical, so we communicated that to the other telescopes. Fermi did a follow-up on it, and a day after, it saw an increase in the gamma ray activity of the source. So there was a gamma ray flare, and then the MAGIC telescope, which works at higher energies for gamma rays compared to Fermi, also identified the TV gamma ray emission in the direction of that source. The chance of coincidence for TXS for having these two coincidences by accident rejected at the level of 3 sigma. And you can see the localization of the event and where the source was found. Interestingly, we looked back now that we knew there is something interesting in that direction in the sky into our archival data, and the time-dependent search in the direction of TXS revealed another neutrino flare in 2014, which was actually dominating the flux in the direction of TXS. The flux came with about 13 neutrinos, rejecting the background hypothesis at 3.5 sigma. And surprisingly, but kind of consistent with the idea that you need a dense environment for the production of neutrinos, this was not accompanied by a gamma ray flare. You can see the morphology of the neutrinos here, and you can also see how the width of the flare was identified in the top plot here. This actually, the absence of the gamma ray emission became an actual emerging feature in the coincidences that we see for the other alerts. So this was the TXS that we discussed, the Big Bird, and which is one of the PeV neutrinos that we see is coincident with another blazar. And also another coincidence was reported for this blazar. And if you can see here, they are all in a quiet mode in terms of the gamma rays. Before and after of the alert, the gamma ray activity is higher. As a result, opaque sources are becoming the primary candidates for high-energy cosmic neutrinos when it comes to AGN. Another important component to the high-energy cosmic neutrino flux is the galactic cosmic neutrinos. The galactic neutrinos were considered as a guaranteed component. However, as you see, they are subdominant to the extragalactic component that we see. But we know that the bulk of cosmic rays that we see on Earth are from the galaxy. And we know that the cosmic rays up to the knee are galactic in origin. So the pivotrons, the cosmic accelerators in the galaxy that can produce particles up to PeV energy exist, and they are producing cosmic rays that go to the molecular clouds and the dense environments in the galaxy and produce pions, which will eventually decay to neutrinos. This is a sketch here. Supernova remnant is one of the primary candidates. The shock accelerates into the dense molecular clouds, and then you will have neutrinos. This is basically cosmic rays diffusing in the galaxy, going to the interstellar medium. After diffusion, they will produce that. They will interact with the environment, and then they will produce charged pion and neutral pions. They will produce TeV, gamma rays, and neutrinos. After 10 years of data, using cascade events, this time not the tracks, IceCube was able to identify galactic component of the high-energy cosmic neutrino flux by rejecting other hypotheses at 4.5 sigma. We utilized 3 different models that used the distribution of matter and sources in the galaxy. And as you can see, most of them find at the level of 4 sigma, so we cannot really distinguish between these models. But today, we have the first picture of the galaxy in neutrinos. This will enable us to search for more cosmic ray accelerators there. Another important part observable in high-energy neutrinos is their flavor. Flavor can provide a lot of information for the neutrinos based on the standard oscillation. We expect that whether it is muon damp, neutron decay, or pion decay, the neutrinos would oscillate into equal portion of each flavor. So the fraction of nu tau, nu mu, and nu e at Earth would be basically within this butterfly that is defined by the dashed line here. If this is not observed as such, it will be indicative of new physics. And because of that, the cosmic neutrino flavor acts as a very powerful tool to search for new physics. The current sensitivity is not good. You can see the 68% contour for the measurement, and the best fit here basically covers a large portion of this triangle. But with more data and better identification, this contour will shrink, and future detectors can deliver much more accurate measurement here. An important development is identification of tau neutrinos. Tau neutrinos are very special. They are a very limited number of them have been so far observed. And you can see the list for do not, opera, and super K here. But for IceCube, at very high energies, tau neutrinos are very rare in the atmosphere. So if you see a tau neutrino, it is astrophysical origin. Because of that, it's very important. And it was discussed, they will leave a distinct morphology, but creating two cascades in the detector. When we look at the individual digital optical modules, we see two distinct energy depositions in the detector, in the DOMs, as you can see here, and that's indicative of production and decay of tau. Using machine learning techniques, we have now identified 7 tau neutrinos in 10 years of IceCube data, which is actually compatible with the number of tau neutrinos that you would expect from the astrophysical neutrino flux. Another important feature to identify the flavor of astrophysical neutrinos is the glacial resonance. It happens when an anti-electron neutrino interacts with an electron inside the ice, and then produces a W boson. The W boson decays and creates a resonant feature in the cross section. This was identified in a partially contained PeV search in IceCube, which deposited about 5.9 plus 0.18 PeV energy. The reconstructed energy is compatible with what you expect for glacial resonance. Now that we talked about the observables of high energy neutrinos, we need to comment on the fact that these observables are powerful tools to study new physics in the neutrino sector. We can study them based on the arrival direction, the flavor composition, temporal information, and energy spectrum. You can see a lot of new physics scenarios here, and you can see by the lines that go to each of these observables where they get some influence. And here I will briefly discuss dark matter annihilation and decay. Before that, let's mention why new physics in the neutrino sector benefits from high energy neutrinos. It is they have the highest energy, which means that you can probably new physics at the new energy scale. You have a long baseline, so you can accumulate on those tiny new physics features. And they are basically interacting and carry quantum number, which is the flavor. And of course, they also come with higher statistics and complementarity with the laboratory experiment. The neutrino portal to dark matter is actually very interesting. We do search for dark matter in 3 different ways: by producing them, by direct detection, which is basically dark matter standard model scattering, or by looking indirectly for the production of dark matter decay or annihilation. And the thermal wind production in the early universe implies that self-annihilation or decay might be ongoing and possible. We do have a stronger constraints placed by the X-ray and gamma ray observatories, but the neutrino protocol remains important and is the most invisible channel, hardest to detect and difficult to rule out. IceCube has done this search regularly on Taurus, and other detectors also do this. You can see the decay and the annihilation limits for the neutrino channel and tau channel here in this plot. And IceCube, as I mentioned, is not alone, and the very heavy dark matter mass is actually the territory of the neutrinos. This is the only, this range is only accessible to neutrinos, and as you can see, the best limits here are provided currently by Antares and IceCube, and in the near future, the upcoming neutrino telescopes will provide limits that are close to the thermodynamic abundance. The landscape for of neutrino astronomy in the future is quite bright. We have 4 detectors coming up in the northern hemisphere, and in the near future, we will add to the total volume of the neutrino telescopes. It is very valuable in terms of increasing the statistics and better exposure also to the southern sky. And in the next decade, we will have IceCube Gen 2, hopefully, which will increase the size of IceCube by a factor of 10, giving us a reach to EV energies. This will happen in multiple stages. We are now upgrading, adding more arrays to IceCube. The IceCube optical array will enhance the current size, and the radio array that it will be on top will give more access to EV energies, eventually giving us a factor of 5 better sensitivity for the sources. In summary, after a decade of observation, signs of anisotropy have emerged in IceCube. AGNs appeared as the primary candidate sources for the high-energy cosmic neutrino flux. It is compatible with the features that we see in IceCube, and the observation of the galactic components opens new ways to understand cosmic ray acceleration and cosmic ray accelerators. These all open new avenues to study new physics and dark matter searches with the neutrinos, and hopefully with the upcoming neutrino telescope, we have the opportunity to increase the statistics and significance of these observations. Thank you.